Our next speaker is Geoff Chih-Fan Chen from UCLA, and he'll be talking about lens modeling and time delay prediction of J0924 strong lens system with Keck AO data. So take it away, Geoff.
Hi everyone. Can you hear me?
Yes, we can hear you and we can see your slide.
Okay. Yeah. So thanks. Okay. Thanks for the organizer to give me the opportunity to give a talk here. So I changed a little bit the title with High Data Cosmography with Keck. Okay. So my name is Geoff Chen. I'm a postdoc at UCLA. So I'm working inside the TD Cosmo collaboration, which consists of the Holy Cow, the Sharp, Cosmogral, and also the Strice. Okay, so I will talk about the state of the art of Echna attention and what's the rule of the Echna, the Keck in measuring the Echna. And I will talk about a summary in the end. Okay, I think that there is a little doubt that there is a Echna attention, especially if you compare with the early universe readout from the CMB swimming lambda CDM model and with the measurement from the late universe. So you can see that all of the different methodology measure the higher Echna. So you can see the systematic shift to the right. And if you combine them all, then you can see that there is like a 5.7 sigma tension with the early universe. So even you compare with different, combine with different like a Cepheid, TRGB, or Mirus, so they are all consistent with about 4 sigma. So because we are observer, this is a Holy Cow readout here, and because we are observer, we are doing the modeling, we are always worried about the systematics. So, so then we are doing, recently we are focusing on really serious about the systematic check. So especially relaxing assumption of the mass profile. Just to mention that the Holy Cow previous work using the industrial-like mass profile to constrain the galaxy by extended imaging. So first is a power law model. The second one is a model consistent with NFW profile plus a star, which has a constant mass ratio. And then the result is like a 73.3. And even we separate the power law and NFW profile, we found that the result is quite robust. And then the TD Cosmo 4, so recently we relaxed the assumption of the mass profile, and you can see the uncertainty blow up. So like a 74.6 plus minus 6. So it's almost like 8%. And if we want to use the external data set like a SLAC lenses, which we can have the velocity dispersion information to constrain the mass, further constrain the mass profile, and then the prior from the SLAC lenses drive the value to the lower value now is consistent with the CMB, but also with consistent with Cepheid because the uncertainty is larger. But then one of the assumption of this purple readout here is that the SLAC lenses are drawn from the same population of the TD Cosmo lenses. But you can but the SLAC lenses is live in the much more lower redshift. So then the question turns to that we want to build more lenses and also have more galaxy mass profile, which more consistent with TD Cosmo lenses. Okay, so now I'm talking about the AO. What's the Keck rule in measuring the Echna? What's the benefit and what's the rule? So if you compare with the AO and space HST imaging, the readout from these two, you can see that the AO have better precision than the HST, especially because the 4-week half max of the PSF is smaller and the resolution is higher. So then the two of this benefit further constrain the mass profile, so we can get tighter constraint. And from Echna from the Keck AO, we can see that there is if we use the three lenses from here, we can have already like a 4% uncertainty on the Echna. And then so now we are building up more and more lenses. So this is another one is currently in progress at J0924. So the first three raw is the HST data, and the final, the last one is the Keck AO data. So this is ongoing, and because currently there's like 50 lenses has already discovered by the DES. However, only like more than 80%. More than 80% of lenses either too far south or lack of tiptoe star. So the KAPA is very important. The KAPA within the Keck AO sky acquisition adaptive optics. So it can increase the sky coverage, and that's why we can get more AO data on the ground. And this is a part of the sharp summary figure. So this is you can see that only 4 lenses is from lens quasar is from the sharp summary figure. So now we are building up, trying to building up more and more lenses, tinier lenses in the sharp. So another thing is for the spatially resolved kinematics, because this is particularly important when relaxing the assumption of the mass profile, because the mass velocity dispersion can prop a different area of the lensing galaxy. So you can have further constraint of the mass profile, especially if you relax the assumption. So from here, if we have the 7, now we have the 7 TD Cosmo lenses plus the AO IFU, we can reach like 2.5% if we have the IFU data, 50 lenses IFU data. And then if we have 40 tiny lenses, and then we can reach 1.2. If we have like 200s, lensing gas use the IFU data to further constrain the mass profile. So the OSIRIS, so now we are currently working on OSIRIS to study, to constrain the kinematics, and future Leica with KAPA will be a great resources. So the summary is here. So the dedicated tiny data program can reach 1 or sub% precision on HNA. And we have already shown that the HNA, Keck AO can deliver pretty good imaging quality and constrain the mass profile and hence the HNA. And the next generation, the KAPA will be the key to achieve 1% on HNA measurement. Okay, thanks.
Thank you, Geoff. You mentioned LIGO in the previous slide. Which feature of LIGO is going to be the most advantageous? Is it the spectral resolution or is it field of view?
I think the spatial resolution, and especially also the higher signal to noise from the KAPA. Yeah, so that's very important because now the difficulty of using OSIRIS is the signal to noise is really low. Even we integrate like a 2-hour, so it's really hard to extract the absorption line to get the velocity dispersion of the lensing galaxy, because one of the reasons is that the lens quasar is so bright. And that's why we really need the Leicas to have the high signal to noise and spatial resolution, and yeah, to get the velocity resolve velocity dispersion. That's very important, especially if we relax the assumption of the mass profile.
Other questions?
Josh, I have one.
Go for it, John.
Is there a particular type of, and I'm sorry if you address this, or is there a particular type of lens system that you're really ideally looking for? Most of the lenses that you had are fairly similar in their geometries, and I'm wondering if there's sort of an optimal type of lens that you're looking for, because the number of lens systems is going way up as these machine learning and neural networks things find them, and I'm just wondering if there's specific one, if there's the perfect type of lensing system that you could have, what would it be?
If we don't think about relaxing assumption, then if we have a specific lens with a higher, longer height, that will be important, because with the AO and HST imaging, then we can pretty good constrain on the mass profile, but then the dominant will be the time delay. So if you have like 100 days of time delay between the imagings, then if the uncertainty like 1 or 2 days, then we will reach like a 1%, 2% of the time delay. So if you have if you have a lens with like 10 days uncertainty, that you have plus minus 1, then it means that it's 10% uncertainty. So they will translate to the HNA with 10%. So I think that the longer time delay is important. particularly if we don't assuming the relaxing assumption of the mass profile. But if we relaxing assumption of the mass profile, then the building up the sample size is more important than particular length. And then also, if we can access more kinematics information from different galaxy, TD Cosmos-like galaxy profile, then the prior from the population can further constrain the H0. So yeah, this is a different point, perspective.
Great, thank you, Geoff. I believe it is time to move on to our next speaker.